Welcome, everyone. Welcome to the WITS workshops. I will be your MC today. My name is Lina Mariette. I am a scientist with a PhD in physics. I'm also an entrepreneur, and I'm a consultant. I specialize in helping women who want to make a career switch into the amazing world of data science and AI. You can connect with me on LinkedIn using the link on the screen right now, or the handle on the screen right now. In today's workshop, we're going to have an approachable introduction to all things AI. Our instructors are going to show us how to break down the buzzwords in artificial intelligence, but that's not all. Also, we're going to learn about real-world use cases. Without a question, I think this is an important topic for many of us. The title of the workshop is Demystifying the Jargon and explore the history behind this groundbreaking technology, and will be presented by Erin Stanton and Kathryn Novak. So let me tell you a little bit about Erin and Kathryn. Kathryn currently leads the U.S. Client Services team for Virtu Analytics. She is currently based out in New York, but was based in London for the past year. Kathryn has her Series 7 license and holds a BA in mathematics from the University of Virginia. And Erin is a leader in the field of data science and big data, and is known for her big energy, which she brings to every chance she does. I love that, Erin. She has over 15 years of experience in the industry, and she earned an undergraduate degree in computer science and economics, and also holds a master's degree in information and data science from UC Berkeley. Erin and Kathryn will be answering your questions, so please add them into the Q&A as we go. And without further ado, please welcome Erin and Kathryn.
Hi, everyone. Good morning, good evening, good afternoon, wherever you're dialing in from. Kathryn and I are on the East Coast, so it is 11 a.m. here for us. Today is what we're calling AI 101, and it's really here to give you a basic introduction to several topics across AI and machine learning. This is intended for beginners, so we're going to give you a lot of different definitions. We're going to take it from the perspective that you're brand new to AI. If you're not a beginner, you're welcome to stay. We do cover a few more detailed technical topics, but this is intended to be a beginner's presentation. Please make sure you put your Q&A. Amy already plugged you guys. Please make sure to put it in the Q&A bot. I will be monitoring it throughout. Kathryn and I love to take questions as we go through, so we're happy to take those. Let me go ahead and share my screen. Just give me 2 seconds here so I can figure this out. This is hopefully the hardest part of my day. Screen share. Okay, I think we're up. Kathryn, do we look good?
Yep, looks good.
Okay, so I do need to preface a couple things probably before we jump in. Kathryn and I have a few things that we love, and they may or may not come up in today's presentation. We both love Taylor Swift. We are big Swifties here in both this presentation as well as in my group, so she may or may not come up. And then I also have 2 dachshunds at home, and so they may or may not come up as well. So what is AI? Let's jump into the good stuff. So at its core, AI is really all about creating computer systems or machines that mimic human intelligence. So we're really trying to recreate the amazing human brain that we already have. It's important to understand that we're trying to reproduce basically the capabilities of our brain. That includes our visual perception, right, our speech recognition, and our decision making. So what is covered under the AI umbrella? We have machine learning, which is where we're going to spend some time on today. We have natural language processing, we have computer vision, we have robotics, we have speech recognition, and generative AI. And there's other groupings in there as well, but these are some of the main ones. AI is really, it's not an abstract concept at this point. It's real, it's a growing part of our world. It's what I spend a decent amount of my day job on, building ML and AI models. And so as we continue to explore the possibilities of AI, it's important for all of us to understand its potential and its implications, right? Its implications on our careers, its implications on our own personal lives. And that's really why we're here today. So I'm going to hand it over to Kathryn to help us distinguish between those terms of AI and ML.
Thanks, Erin. Yeah, let's talk about the differences between AI and machine learning. They're often used interchangeably, but they're actually not
I
the
use
same.
them interchangeably. I'm
Yeah.
really bad about it. I just used it there interchangeably before when I was
Yeah.
like, I'm really only doing machine learning. I'm not doing AI.
It's easily done, right? AI is really the umbrella term for the simulation of human intelligence in machines, as Erin was saying before. And AI uses multiple approaches to build that intelligence, where machine learning is more the subset of AI, right? It's kind of like the square versus rectangle situation. Machine learning is a subset of AI based on statistical models and data analytics. So if you're going to remember anything from this session, remember that machine learning is data driven. So let's dive in a little bit deeper on machine learning, which again, is a big focus of today, right? So machine learning is the idea that machines can learn from data, identify patterns, and then make predictions. So machine learning models have a remarkable ability to learn and improve without being explicitly programmed. But what actually is a model? So a machine learning model is a mathematical function trained on data to make automated predictions and decisions by detecting patterns and learning relationships between inputs and outputs. As a result, trained machine learning models can make predictions or forecasts about future events and estimate unknown values by applying what they've learned from data to new situations they've not encountered before. So a real key advantage here is that they can make automated predictions and decisions without needing to specify explicit rules and logic. So machine learning has enabled breakthrough capabilities in many applications, such as image recognition, language translation, personalized recommendation, all that kind of stuff that we're going to dive into deeper later in the session. But by leveraging the power of data rather than by just using traditional programming. And so the ability to continually learn from new data means that these models can improve their performance over time. So we have a few key terms that we kind of want to go over before we really dive deep into machine learning. So the first one being overfitting. This occurs when a machine learning model fits the training data very closely, but fails to actually generalize well to new data. So this happens when the model is too complex relative to the amount of training data available, and the model essentially memorizes the noise and the details in the training data set, rather than actually learning the true underlying patterns that are needed to make predictions in the new data. Underfitting, on the other hand, occurs when the machine learning model is unable to capture the underlying pattern in the data because it's too simple, right? It hasn't learned the true relationship between inputs and outputs, and an underfit model is going to perform poorly on both the training data and the new data because it doesn't know what the pattern is, right? It doesn't have the pattern required to make accurate predictions. So increasing that model's complexity is what's going to be needed to improve the performance on both the training data set and the test data set.
And in practice, I would say we're typically much more concerned about overfitting. It's rare that I run into an underfitting scenario. Usually I want to control things so much and I'm giving the model like 30 features, right? And I'm like, oh, learn from all of this information. And it essentially memorizes things instead of learning. So overfitting in practice tends to be a much bigger concern.
Yeah. Another potential issue, right, is bias, which refers to the mistakes that arise from erroneous assumptions in the machine learning system. So this leads to consistent errors because the model is oversimplifying yet again and making incorrect generalizations about the relationships between the variables. So bias can also cause the model to systematically miss patterns and results in underperformance on both the training and new data as well. So here, careful model selection, training techniques, and feature engineering is what's required to reduce bias and improve the model's assumptions and ability to learn the relationships in the data. Features are super important. Features refer to the specific variables or attributes from the data that are fed as input to the machine learning model. So I think this was something that I had to kind of get my mind around.
It drives me nuts. We don't just call them model inputs. That's literally
that's
all they are. But we had to come up with a fancy name and call them features.
Yes. Yeah. So that's really what features are, right? They're the inputs. So we need to select informative, relevant features, and that's crucial for training an accurate ML model, as the model learns relationships between the features and then whatever the target variable is. So careful engineering and selection of descriptive features that are relevant to the target output is key for building effective machine learning systems. And then the final term I'm going to leave you with is accuracy. And this is the key evaluation metric for assessing the performance of your model, right? How did we do? And so it refers to the proportion of correct predictions made by the machine learning model out of all predictions. So this is when you use it on your test data, right? You want to see how well did my model predict on my test data. So a high accuracy indicates that the model is able to reliably predict the target classes across all various inputs, and maximizing accuracy involves tuning the model architecture and parameters so it can learn the patterns from the training data and generalize well. So I know that was a lot. So the TLDR here, right, is overfitting is training the data too closely. Underfitting is failing to recognize the pattern. Bias are systematic errors due to poor assumptions. Features are the input variables for the model, and accuracy is the fraction of correct prediction.
Awesome. I love it. So we are trying to make this as interactive as possible, even though it is a lecture. So we're throwing in two different polls here, which is our interactive component. So what we're doing here is we have 3 students. So they all go to the same college, and let's just say that they're all enrolled in a computer science 101 course. So the 3 students we have Jen, Beth, and Sue. So Jen she's really not interested in learning. She's not really excited about computer science. She gets a 50 on the class final. And when we test her on her general knowledge of computer science, so like a general, let's just say, test we get off the web, she gets a 57. So 50% on the class, 57% general knowledge, really not interested in learning. Beth, on the other hand, loves this course. She sits in the front row. She's super excited. She memorizes basically absolutely every word that comes out of the professor's mouth. She gets a 98 on the class final, but when she's tested on her general computer science knowledge, she doesn't do as well, and she scores a 67. So instead of learning the concept, she's basically just memorizing every word that the professor said. Lastly, we have Sue, who is more of kind of a conceptual learner. Sue gets an 85 on the class final, and she does slightly better with a 92 when tested on her general knowledge of computer science. So based on the definitions that Kathryn just gave, which one of our 3 students, Jen, Beth, or Sue, shows the concept of overfitting when it comes to learning in this computer science 101 course? Amy, can you pull up that poll? Poll number 1, please. Okay, so go ahead and put your answers in here. So is it Jen, Beth, Sue? And it's also okay to not be sure, right? We're all here in a very friendly learning environment. If you're not sure, just say not sure. So we'll give you guys a second here to put those questions in. I'll give you about 10 more seconds here. Okay, Amy, can we see the poll results? Awesome. Great job. So many of you got that it was really Beth, right? And it was with that terminology of memorizing. And we also see there that Beth really, right, she memorized that class content so well. But when we tried to get her to generalize her knowledge with that just general computer science test from the web, she really didn't do well. So that's really the concept of overfitting here. I'm memorizing what happens to me in class, but when I try to take those conceptual concepts and apply it to something else, I don't generalize well. Sue is probably where we want to land, right? So she does pretty well on the class test. She does even better on that general test, and she's a conceptual learner. When we're building models, we want them to really kind of be conceptual and not memorize what we show them. Awesome. Good job. Great job, everyone. So I'm going to hand it back to Kathryn now to take us through how we actually develop an ML model.
Awesome. So now we have a basic understanding of the key terms here, right? I think you guys did a great job on that poll.
Yeah.
Now let's see, what does it actually take to develop an ML model? All ML models kind of go through the same life cycle. They all start the same way, and that's with data collection. So we're going to gather the relevant data sets required to train an AI model, and this can include things like images, text, audio, videos, etc., any type of data. So as we kind of talk through the life cycle, we're going to go through an example here together, which is a housing price predictor. So in this example, I'm going to pull data from the US Census Bureau, and I'm going to need to collect historical housing prices, right? Because that's what I'm trying to predict. But I'm also going to pull any relevant data around that, anything I think that might help me predict a price. So this could be house size or, number of bedrooms, number of bathrooms, all that type of stuff.
So Kathryn, I was reminded by one of our Canadian colleagues, because in this predicting house prices, I always think of Zillow, right? The home price, or like the home buy and sell app that I have on my phone, how we actually found the house that I live in now. They have predicted prices on that, but I didn't actually realize that Zillow is an American only concept. Our Canadian colleagues reminded us that. So here we're really trying to say, wherever you live, when you go out to buy a house, sometimes there's applications that say, we predict this house should cost XYZ. In the US, it's really common and prevalent. In our apps, it might not be as prevalent outside of the US though.
Yeah, and so here we're trying to build one, right? We're trying to build the infrastructure for that type of app. So I've collected my data, right? But that doesn't mean that my data is clean and ready for a model. So now I'm going to go into the data pre-processing stage. So this is cleaning and preparing data for the model, which involves feature extraction, data labeling, that kind of stuff. So this could be, categorizing houses into size buckets or neighborhoods, or maybe even type of home, like apartment versus single family versus condo, something like that, right? Anything I might need later on. I also, during this step, do exploratory data analysis, which is the process of performing initial investigations on the data to try and discover patterns and spot anomalies, maybe test a hypothesis or check your assumptions. And EDA enables a better understanding of the data characteristics and helps to identify important variables to build our predictive models. So in this example, we're actually plotting the distribution of housing prices. So we've kind of bucketed them into, different groups, and then I'm plotting them. And so I want to see how prevalent are different prices. So if I'm seeing a ton of houses that are like less than $1,000 and a ton that are more than $1 billion, I know something's wrong with my data, right? That's
a data issue.
Yeah. So I may need to go back to my data collection, either recollect it or maybe check my units, right? Maybe these have been, divided by 1,000 or 1,000,000 or something like that. So here's where you can kind of check your intuition, make sure your data makes sense for what you're looking at. And once I feel comfortable with my data, I can actually start picking out my features, right? We talked about features before. So here I'm going to select, like, what actually am I going to use to include in my model? And these, again, should be intuitive, right? In this case, I might use total square footage, lot area, garage area, right? Things that I think are going to directly impact the price of a house. I'm not going to use things like color of an interior wall, right? Like those things can be easily changed, don't make an impact on the house price. So I'm checking my intuition again here. So,
and this is where actually in one of our other, when we held our own WIDS conference, a couple of the participants who didn't have backgrounds in data science, they actually had humanities degrees, but they're contributing to AI processes. What they were bringing to the table was their subject matter expertise in the fields they were in. You need this intuition component, right? Where architect is saying, no, do not include the color of the wall in a house. That's easily paintable. Right. No one is going to include that in the factored in the sales price. So there's components of where you have the more technical data scientists contributing to an AI model, but you also need subject matter expertise that might come from humanities, history, English, all those great degrees.
Yeah, for sure. You kind of need a well-rounded team looking at your models.
Yeah, that came up quite a bit. This team is, and we have our own teams. When we build ML models, no individual at our group builds them in isolation. We have a team of at least 2 to 3 people that contribute, and then we call in a team of what we call, it's a peer review, where we basically have people who are subject matter experts, but they didn't physically touch the model, and they also then add their intuition to the process.
Yeah, very important. So once you have your data, you've selected your features, we're now going to feed them into a model, right? So we need to select our model. This could be linear regression, which is really modeling the relationship between dependent and independent variables using a linear equation, or a random forest that averages predictions from many decision trees, trained on random subsets of data and features, or XGBoost, that converts weak learners to strong ones by iterative training and weighting to optimize predictive accuracy, right? Depending on your data set, you'll pick a different model here, and you may need to try a couple before you actually get to your final result. But once you've selected your model, you can start training it. So you're feeding that process data into a machine learning model and training it by optimizing its parameters. So there's a couple different training methods that are pretty popular. It can be supervised, unsupervised, or reinforcement learning. And Erin's going to go into a little bit more detail on those three a little later. But once I've, selected my model, I've trained it, again, may have to iterate that through a few times, but then I'm going to evaluate my model. I want to see how accurate is it. So I'm going to test the performance of the trained model using a sample test set, something that the model has not seen before, didn't get trained on this, to identify any errors or opportunities for improvement. So testing the performance of the model, we're going to use some sort of an accuracy evaluation. So this could be, mean absolute error, mean squared error, variance score, any of those types of numeric metrics. And then I'm also going to do another intuition test here, right? Like I'm going to put my human eyes on my result to say, does this actually make sense? So once I'm comfortable with it, right? And again, that takes a long time to get to that point. We're then going to deploy our model, right? This is a long time down the line in your machine learning development, but we're going to deploy it. We're going to put it into production. So this means, putting it in an app or putting it on a website, getting it to your end user. And so once that model's live, it starts to get more and more data, right? As it's used, we can collect that new data to incrementally train and improve the model to adapt to the changing real world conditions, right? Housing prices change over time due to inflation or, any type of real world condition. So we want our model to learn from that. We don't want to be using outdated prices. So constantly feeding new data back in is helping to create success of our predictions. And so that's why we think of this as a life cycle and a continuous learning cycle.
So we did get a question here live in the Q&A that I wanted to jump in and answer. So can you achieve a really good fitting like 98% and that model be successful at prediction or not? Or is 98% basically imply that you have overfitting? So I will say that was probably a big learning experience between my academic ML and my real world ML. We were absolutely in the academic setting getting models that were well over 98%, right? We were whittling down close to even 99%, and they weren't overfit. The big difference I would say between academic and the real world is in the real world, if you had features that perfectly described your data, you had the perfect inputs, 98% is achievable. You just do not have that data. We have fantastic data at our firm. We feel like we have pretty good features. We're not coming close to 98%. And it's just because we don't have data that captures every single component of a life cycle. And when you think about this housing example, right, maybe you have the square footage of the house, maybe you have the location of the house, maybe you just don't have, if the house has a yard or not. That's a really important feature, probably, but you just don't have it available in your data set. That's really what holds you back from getting that 98% as opposed to overfitting. We absolutely, though, in the academic world got close to or better than 98%. And that was a real eye-opener when I then got into the real world and I was like, this isn't even close. Like my model stinks. Your model's still good. Okay, so machine learning, right? We just kind of went through hopefully a really good example and you feel a little more comfortable with it. But machine learning is all about enabling computers to learn and improve from experience without explicitly being programmed. So without me giving it explicit rules, when you see that a house has a garage, add $100,000, right? When you see that a house does not have a yard, subtract $50,000. That's what we're trying to avoid. We want it to learn directly from the data. So there are several types of machine learning models, which can basically be categorized into three main groups. At least this is how I think about it. You might have learned it differently, but we have supervised learning, we have unsupervised learning, and we have reinforcement learning. Supervised learning is definitely the most common approach of machine learning. It is also typically the preferred approach of machine learning. In this approach, the model is basically trained on labeled data. So if you think about a really simple example, you're training a model to identify photos of dachshunds. I told you they would come up. So I want a dachshund spotter model. And so I show it photos that have dachshunds in it and I label it. And I say, this has a dachshund in it. I show it another photo that has a dachshund in it. And I say, this has a dachshund in it. I then show it a photo of a cat and I say, not a dachshund. So I'm giving it examples that it can learn from, but I'm also telling it essentially what it's learning. Dachshund, dachshund, not dachshund. So the goal is basically to allow the model to map that input data to the correct output labels. Supervised learning is then also basically divided into two main types of tasks. So we have classification, where the model is basically predicting discrete categories, so that dachshund, not dachshund, right? That's discrete. It can either be dachshund or not dachshund. It's one of two options, and you can have more categories, but it's basically categories that you're predicting. Or you can predict continuous variables, and we do both in our own space. We probably spend a little more time in the regression space, which is where I'm predicting something like 0 up to infinity, right? If you're doing a weather prediction app, that's going to be a continuous variable. The housing price, that's going to be something that I'm going to actually let you think about, and I'm not going to give you the answer for that. So the housing price example that Kathryn showed before was supervised. We had the prices of past houses that sold, and we had all of these different features. It has a yard, it has 4 bedrooms, it has all these different things. And we use that alongside the features to train that model. So I almost gave away the answer to our second poll. So based on those definitions that I just gave you, what was that housing price model? Is it classification or is it regression? Amy, can you go ahead and pull up that other poll? So classification, regression, and it's okay to not be sure. All here to learn. We'll give you a little bit of time here. Okay, Amy, can we see those poll results? Whew. Regression. Yes, we are trying to predict a continuous variable. The house price could technically be 0. That house price could also be $1 billion. We're not sure. It is continuous. It is not, it's not 0 or $1 billion. It's some sort of variation there in between. So really great job there. Before I move on to unsupervised learning, I did want to answer 2 other questions that came in here. So I'm going to say answer live on both of these. So one of them, I'm actually going to go back to my previous slide on, was a question on feature selection. So what's the best technique to select features, SHAP or inbuilt feature importance? So SHAP is a fantastic library that will give you great feature importance. So the most important features of your model. Not all features, though, you can actually run feature importance on. There's different techniques. You can use PCA, you can use SHAP, you can use just out-of-the-box feature importance. I think probably the most important tool that you have for feature selection, though, is your intuition. Is you need to get really familiar with your data and use your intuition to decide which features to start with. There's then other various techniques you can do to kind of tweak. Should I include this one feature? Should I not include it? There's other techniques that you can do. But I think personally that your intuition matters the most. As Kathryn said, I had a purple bathroom when I moved into this house. Did it affect how much we bought the house for? Nope. We just painted that day one of moving in here. So there's different types of features, and I think the intuition is probably the most important. And then how are metrics thresholds defined at the workplace, and how are stakeholders discussing this issue to validate a model for deployment? So for us, we do a combination of that peer review, and then again, our subject matter expertise. So depending on the model and depending on what we're trying to predict, we will have different thresholds for acceptance when it comes to the accuracy that we're willing to accept. That typically comes out in the peer review process, where the model builders present everything that they did. They'll present their assumptions, they'll present the data they used, they'll present, more importantly, the data they didn't have, which they wish they had. They'll present the features that they actively excluded. That all comes out in our peer review process. As part of that peer review process is typically where we define thresholds by model. It is absolutely by use case. We have some use cases where we see much higher accuracy, and we have other use cases where we have lower accuracy, and we're okay with that. So that all, for us at least, comes out in our peer review process. Let's jump back to definitions, though, because we cannot forget about poor unsupervised learning, which does not have labels. It wishes it did, but it does not. So this is where models are really trying to find hidden patterns within the data without you explicitly giving it kind of categories or outcomes to learn from. So a really common unsupervised learning techniques, they include clustering, which is basically where you're grouping similar data points together, dimensionality reduction, which aims to reduce the number of features in the data while still preserving its essential structure. That's one thing that you can use for your feature selection process. But a really easy, I think, to understand example of unsupervised learning is actually what Spotify does to build your weekly recommendations. So if you're outside of the US, I don't know how common Spotify is. Kathryn and I are diehard fans in the US. It is a streaming music app that you buy a subscription for. And what they do every single week is they post a new playlist to your account. And it says Erin's weekly playlist. And I go in, and most of the time, I'd say 9 out of 10 times, I'm like, ooh, these are some good songs. I like these. How they're doing that is they basically look at all of the music that I've listened to historically, and they'll say, you know, okay, Erin, 90% of the music she's listened to historically is Taylor Swift. They'll then go and look at, with a little true crime podcast mixed in there, they'll then go and look at Kathryn's Spotify, and they'll be like, oh, interesting. Kathryn also has about 90% of her music as Taylor Swift with, what else would you have mixed in there, Kathryn?
Pop culture podcast.
Okay, so she has some pop culture podcasts, and they'd be like, Erin and Kathryn seem similar enough. We're going to put them into the same grouping of similar music listeners. To then create that weekly playlist for me, what they do is they look at songs that Kathryn has listened to that I haven't listened to, and they just suggest them to me. So that's a really common way that people are using unsupervised learning. So, you know, if you see anything, if you're in any sort of streaming app, any sort of Netflix, which I know they have outside of the US, any sort of Amazon playlist, all of those are by doing this kind of similarity search between these two people are pretty similar. Let me recommend stuff to them that this other user has liked. So reinforcement learning is a bit different from the first two. In this approach, basically, the model is learning through interactions with its environment. A really good analogy that I use for reinforcement learning is training a dog. So we're currently trying to train our dachshunds. It's going poorly, but we're trying to train them. And so basically, as part of that training environment, I have all these different components. I have the environment, the room I'm training them in. I have the goal, which is to have my dog learn how to lay down. I have reinforcement. So if I say down and my dog jumps up, she doesn't get a treat. But if I say down and she lays down, then she gets a treat. That's basically what we're doing with reinforcement learning, but we're doing it with an algorithm off of data. So we'll put reinforcement learning off to the side, and we'll come back to that in a bit. But typically when we're deciding between supervised and unsupervised, we really would like supervised. So I would much prefer if Kathryn filled out a whole music questionnaire in Spotify and said, I'm a Swiftie, and by the way, I like pop culture podcasts. And I could also go in and say, I'm also a Swiftie and I like true crime podcasts. So we like the label, but we just don't always have labels available to us. So that's why in a lot of cases, we might end up using unsupervised when we would often prefer supervised. So for the next couple of minutes, we're going to blast through various types of models. You might get a little whiplash, but hang in there with us. These are possibly models that you may have heard of, and we want you to have a high level conversational understanding basically of each. So let's take a closer look at one of the more powerful and widely used models in machine learning, which is neural nets. So neural nets are inspired by the structure and function of our human brain. They consist of essentially layers of connected nodes, which are called neurons, and they're similar to our brain cells. Information flows from these neurons, getting passed from one layer to the next, just basically how signals in our brain work. So one of the major advantages of neural nets is really their ability to recognize patterns that are often too complex for either our brain or other algorithms to identify. This makes them great for tasks like image recognition, speech recognition, where these patterns can be highly intricate, right, and subtle. If I have a blurry image of a dachshund, it actually might look like a cat, right? So a neural net might come in there and actually be able to differentiate between the two. Neural nets do have some drawbacks, though. I would say probably one of the biggest drawbacks is you need a lot of data, a lot of training data, so that you just might not always have that much training data available. And they also require quite a bit of computational resource. So you need kind of big, powerful servers in order to train neural nets, and you might just not have that resource available to you. Another potential issue does come with they are the blackest of black boxes when it comes to understanding them. It is really hard to back into why a neural net did what it did. So for us, we actually tend to avoid neural nets because explainability of our outcome is more important for us. So there might be a point where we end up using neural nets, but today we really don't use them that much because we outweigh explainability. We might give up a few points in accuracy, but that explainability is more important to us than those couple of points of accuracy. So Kathryn, I'm going to hand it back to you to take us through reinforcement learning, the training the dog example.
Yeah. So Erin mentioned earlier, right? This is a type of machine learning. And reinforcement learning involves an agent interacting with an environment, then it must learn to make decisions, right? So an agent learns through trial and error interactions, receiving rewards and penalties for the actions it takes. The dog may try and sit instead of lie down and see if it gets a treat for that as well, right? That's kind of a learning there. So the agent is seeking to maximize total reward over time and must balance exploring options and exploiting knowledge. The agent is continuously improving its decision-making strategy based on feedback it receives, and the learning systems learn optimal behaviors without actually having an example data set. There are a few challenges, though, which include reward setting and large environments and sample efficiency. I'm going to come back to Spotify as our example, because again, but Spotify will also actually use reinforcement learning too to try and learn and recommend songs to you. So Spotify wants to recommend songs that users will enjoy and keep listening to on the platform because it increases their engagement. So it can create or formulate a reinforcement learning problem. So it's taking an action, which is recommending a song, to an environment, which is the user preferences, and trying to maximize reward, which is user engagement or listening time. So the model is getting feedback on its recommendations in the form of whether the user listens to the full song, skips it, adds it to a playlist, etc. Right? This is the reward signal. So positive rewards reinforce recommendations that work well. Negative rewards penalize ones that don't engage the user. So me, the big Taylor Swift listener, I may get recommended songs from Olivia Rodrigo. And if I skip that song, Spotify is going to say, okay, maybe she actually doesn't like the pop side of Taylor Swift. Maybe let's go back to the country roots, right? And maybe I'll get a country example. And so Spotify is going to continuously try and give me different suggestions it thinks it will fit and try and get a reward from that. If I then listen to Olivia Rodrigo on loop, they know they got it right. So the model's really trying to explore the different recommendation options and continuously update based on the feedback that the user gives it, so it can get better at predicting engaging songs. This is really an interactive process between the models taking actions, the environment giving feedback, and the model updating to maximize the reward. This allows Spotify system here to personalize and tailor recommendations to its individual user's taste through that reinforcement and the listening signal. We're going to jump again to another AI 101 topic. So,
and Kathryn, I'm going to actually pause you right there and just answer one more question that came in live. We really appreciate all the Q&A. It makes it fun for us. Kathryn and I are not professors. We do not like to lecture. We like to have conversations. So we love the Q&A. So if we use supervised or unsupervised learning methods to develop a system, can it be called an autonomous AI system? So how I view autonomous AI is really where the human had very little to no interaction or engagement with that AI for it to develop. In both supervised and unsupervised learning, there's actually behind the scenes an enormous amount of human intervention. So I more think of autonomous AI as things like self-driving cars, where I'm not, training the model for every single type of technique. I'm letting the model basically learn over time. So in my head, supervised and unsupervised actually has humans' hands involved quite a bit more than what I would consider to be autonomous AI. In my head, autonomous AI is where the human really kind of let that car run into walls multiple times, right? It didn't put the brakes on it, let the car run into the wall. Whereas in supervised learning, the humans, we're actually making an enormous amount of decisions. The features to include, if we want to normalize those features, what data to include, should we cut off the data 6 months ago? Should we cut it off 12 months ago? We're including a lot of information. Our hands are involved a lot more. Okay, NLP. Take us through it, Kathryn.
NLP. So, right, NLP is a field of artificial intelligence that enables computers to understand, interpret, and manipulate human language. So NLP really focuses on programming computers to process and analyze large amounts of natural language data. The goal being to read, decipher, understand, and make sense of human languages that people use naturally to communicate. So this can include speech recognition to convert spoken language to text, as well as natural language understanding to determine meaning. So there's a million things that major NLP tasks do, but some of them are like automatic summarization or part of speech tagging, speech recognition, topic segmentation, all those different types of things. So to actually perform these tasks, NLP systems use linguistics, computer science, and machine learning algorithms like neural networks, which Erin was just talking about. So we're definitely using these every single day, right? The voice assistants like Siri and Alexa use NLP, autocorrect in Word or even, in iMessage, right? They're using NLPs, chatbots, the spam filter on your email, Google Translate, all of these things are using NLP. There are some kind of challenges for NLP, though. They include difficulty in handling sarcasm, jokes, or ambiguous meanings based on context, and also the dynamic nature of human language, right? And trying to learn the slang all the time or different dialects, that can be very difficult for natural language processing. But through NLP, computers are actually able to understand and work with human languages through the application of the computational techniques and machine learning algorithms. It's really powering many of the modern technologies that we interact with daily. So we're going to jump yet again to another AI subject called computer vision. We're moving quickly. So.
We're moving quickly. We wanted to get a lot of introductory content into you all. So in simple terms, basically, computer vision is all about enabling computers to see and understand the visual world around them. So reproduce the human eye there. I will be perfectly honest with you. I've had very little experience with computer vision, and it's probably my least favorite. I do not work well in pixel. I work well in numbers, in data. So I don't do great with computer vision, but we did want to expose you to it. So at its core, computer vision is using basically labeled image data to identify and classify objects, people, actions, text, and more. The goal is to replicate, right, our human vision capabilities and allow machines to interpret and make sense of visual information. A simple example that I already gave was how we can train a model to identify photos of dachshunds. So maybe if you have an iPhone, our iPhone is already doing this, right, in a lot of places. So it has your furry friends as a category on my iPhone. I never made that. It goes through all of my past photos that I've taken of my dachshunds and puts them in a folder for me, which I love. It's a great feature, but that's basically all computer vision that we're doing there. Computer vision could be used to use barcodes, QR codes. If you've used QR codes, that's all computer vision. Recognize faces, organize photos, help self-driving cars. That's all computer vision. So while we are really good, our human eye is actually really good at visual perception, we can really only focus on a limited amount at a time. Computer vision, though, can actually take in a lot of images very quickly. So the reason I'm saying this is I want to set you up with kind of an example of how humans and machines can work really effectively together. So this was one of the first examples of machine learning that I was ever introduced, and it was a case study about how doctors or radiologists, so people who look at X-ray images, were using computer vision models to scan for lung cancer. And so what they found is radiologists that are trained to look at these images of our lungs, they're very good at it. They're able to see a shadow and say, that's just the shadow, that's not lung cancer. Or they're able to actually say, actually, that shadow is lung cancer. This is through a lot of experience and training and learning over time, but they're very, very good at not over-diagnosing cancer and saying this person has cancer when it's just a shadow in the x-ray. Computer vision models, though, that we were training, they were pretty good at going through a lot of images really quickly, but what happened in the initial kind of phase of all of this is they over-identified cancer, and they would say this shadow is cancer, this shadow is cancer. And so they would, if the computer vision was the only thing that identified cancer, a lot more people who actually had it would have been notified that they had it and they didn't actually have it. So one of the great use cases is where you actually have computer vision take the initial scan of x-rays, so they can go through a lot of x-rays really quickly, and then they bubble up any x-ray that they're like, ooh, we need a human to review this. Ooh, we need a human to review this. This helps us get care to people much faster. It helps expand care to maybe people who don't have radiologists at their hospital. This could let radiologists in different hospitals prioritize really urgent cases. So this is a great example of how you're pairing a model with humans, and it was a computer vision example. So I'm going to hand it back to Kathryn now to go through generative. Wow, we really went hard on dachshunds in this presentation.
We really did. I mean, who's surprised? No one.
Yeah, they're so cute.
But this is our final example of AI for our session today. And everything we've talked about so far was about giving computers a human-like ability to analyze, classify, and identify images or text or audio. Generative AI is a little bit different. It takes it a step further and creates new content based on the learned data set. So Gen AI can create new original content like images or videos or text or audio, and it generates that new data rather than just classifying or analyzing the existing data. So some common examples include AI art or text generation or audio deepfakes, right? Generative models learn the patterns in the training data like paintings, text, or voices, and then they use that learned pattern to create new realistic outputs. The outputs might not be completely original or creative, but they aim to be realistic. So I put it into our chatbot and I said, generate an image of a dachshund riding a surfboard, and I got this image, right? So our generative AI used examples of dogs and dachshunds and tried to identify the differences and created a new image of a dachshund. Also learn the relationship of how something rides something else, right? Riding a surfboard. So it knows where to place it and create the image. The other thing is I didn't say, hey, give it to me in the ocean at the beach, right? But the generative AI is also able to put things into context to say, where would a dachshund ride a surfboard? Oh, at the beach, right? And so these are things that the generative AI model is creating. And so then once I have my picture, I think it's so cute, of a little dachshund, I also said, write me a little short story, right, about a dachshund riding a surfboard. So I got the story about Rex the dachshund's big adventure. And again, it's able to create new content. I didn't give it much of an outline, right? But I'm able to get a whole new original story here. So this is the end of our definition section. You made it. I know we covered a ton of different topics and terms. And
we made it, Kathryn.
We made it. Erin's now going to take us back in time to cover the history of AI.
Awesome. So again, I'm not a professor, but I think it's really important for folks to understand the history of AI so that you can kind of understand the decisions we've made already and how we maybe are going to make decisions going forward. So all of this really started in the 1940s. Yes, the 1940s. And this is when some of the key foundations were laid with some of the first mathematical models of a neural net, and that was by Pitt and McCulloch. You then also had in the 1950s when Alan Turing introduced his famous Turing test. So that's basically where we're able to create a machine that is able to produce output that is indistinguishable to a human. So we're all the way back 80 years ago. That's when these concepts were first thought of by humans. The 1950s is when we saw that term artificial intelligence really get coined, and it was the invention of the perceptron, which is really an early type of a neural network. The perceptron was limited, but it did demonstrate the ability for machines to learn and make decisions based off of data. In 1963, we had the development of the first adaptive machine learning system. So this is actually where it was designed to play a game of checkers. So not not Go, not chess yet, just checkers. But it did basically showcase the ability of machines to improve their performance over time. A major milestone was in 1966, and this was really when we had the creation of the first chatbot. So you think ChatGPT, right? You're like, oh, wow, it was only in 2022 that we had that first real chatbot come around. Nope. 1966, the chatbot was called Eliza. Eliza was really it was a psychotherapist tool, so it was used in psychology. It had very limited interactions. So at that point, all of the interactions were hard coded into it. So you would go into Eliza and say, Eliza, I'm sad today. And in the beginning, Eliza would reply and say, oh, why are you sad? I'm so sorry to hear you're sad. But over time, you realize that you were just getting these kind of pre-canned responses. But that was all the way back in 1966. 1972, we had the first intelligent human robot. This was actually developed in Japan. I don't think I get the name right, but I just like saying it. I call it Wabbit 1. It could communicate, it could walk, it could grip objects. And so this was really where we started to demonstrate how AI could physically interact with humans. 1972. So these early interventions, they basically spanned 1940s to 1970s, and they paved the way for the AI that we're doing today. You might be asking yourself, well, how did we go from having a chatbot in 1966, this interactive robot in 1972, the term AI coined in 1956? Why did it actually take us so long then to develop a tool like ChatGPT? And that is where we're going to discuss AI winters. Yes, winter is coming. So the field of AI has really experienced these periods of great optimism, great growth. I'm hoping that we're not in one of these periods right now. That means it's going to be followed by an AI winter. I think we've maybe turned the corner on AI winters and we're not going to have any more of them. But these AI winters are where basically you then have these kind of less optimistic, people get pessimistic about how these can actually be used in our real lives. You have reduced funding in a lot of cases where people get really excited by something and then they're like, well, nothing actually came to fruition about that. And so then we have less funding in that. So the first AI winter occurred from 1974 to 1980, and that was again followed by these kind of initial excitement, high expectations, and then disappointment when expectations fell short. Despite these setbacks, though, that have happened during winters, during that first AI winter, we had a lot of research still being done, and the backpropagation algorithm was developed in that first AI winter. That backpropagation algorithm is critical to training neural nets today. So we still were in winter, but we were still making progress. Second winter happened from 1987 to 1993. This was triggered by the collapse of the Lisp machine. This predates probably many of us here, but you had the collapse of the Lisp machine, and then you actually had a lot of government agencies retracting funding in research and in development of all these. That's okay, though. We still made some progress, and we made some pretty good progress in natural language processing and expert systems. Why is it called an AI winter? I actually don't know why it's called an AI winter, but I would kind of think, in winter, things get cold, growth stops, right? Plants stop sprouting, your trees, all the leaves fall off. So I believe it's probably some sort of analogy where we see, there's not a lot of growth, things are stagnant, things are cold, you don't have a lot of opportunity going on. So the 1990s is basically when we then saw a resurgence of interest in AI as new approaches came out. This really started laying the groundwork for where we are today. Where we made a huge pivot point, though, was in the early 2000s, and this is what you can kind of call this new era of AI. This was all spurred by a couple of things. One was an increase in computing power and really cheap computing resources, right? So computers became really, really cheap. They became really fast. Being able to run big data sets became really cheap. It became really fast. But at the same time, we actually just started saving a lot of data. So companies started saving down their human interactions. They started saving down data across a whole slew of different things. So we have a lot of data being saved, and we have really big, cheap, fast machines. Combination of those is what led to this explosion of AI that we have today. So since the mid 2000s, AI has really experienced this resurgence that we're in today, driven by this explosive growth in the data. I actually used ChatGPT to create this image, but basically what you have on the left-hand side in red is the global data volume, and then the blue is with this investment. So these two paired together, where all of a sudden we realized, oh, we have a lot of data. Oh, data feeds ML and AI. Oh, we have machines that can train models. You saw this kind of pairing where we had a lot of data and we had a lot of investment in AI, which led to the development of tools like ChatGPT. So Kathryn, I'm going to leave it over to you to wrap up. It looks like we have 5 minutes left, so we will try to get to any of the residual questions at the end if there's any time left.
Yeah, thanks, Erin.
Uh-oh. Kathryn's internet has been a little unstable today. Not to worry. Oh, Kathryn, are you there?
I am back. I can
Okay.
get my video back on. This unstable Zoom is not my friend. But I feel like the conversation around AI is constantly changing, right? We're constantly hearing about new bots, new companies trying to get into the space. Constantly.
Literally weekly. Yeah.
And right now, I think we're really experiencing the chatbot race, right? The rapid advancement of conversational AI systems like chatbots and virtual assistants in recent years. And companies are really racing to develop more intelligent bots that can handle human-like conversation, right? So we talk about, OpenAI's ChatGPT all the time, but we actually use Anthropic's Claude. There's also Google's Bard, right? There's so many different ones. I feel like, I open Snapchat now and there's a My AI in there. Everywhere you go,
WhatsApp.
there's a different bot. Yeah, it's everywhere. And so there's really this kind of race to get the best one. And all the advances in NLP and neural networks and conversational AI are enabling more and more natural and complex interactions between humans and chatbots. Chatbots are being integrated everywhere, right? Into customer service, into e-commerce, into entertainment, or even workplace applications, right? To try and make your life more efficient. And so there's the race to create chatbots that are essentially on par with human in their ability to engage in seamless, natural conversations and be helpful for users.
So Kathryn, I haven't seen that Spotify came out with this, but I did see that Amazon Music did, that you can literally type in your mood to an LLM and be like, I'm in the mood for Taylor Swift that's moody plus some true crime, and it'll actually create a playlist off of that.
That's actually so cool.
Right?
I feel like sometimes it's hard to find a playlist that exactly matches what your mood is, but if I can give it a few keywords and it'll create a new one, that's awesome, right?
Yeah.
But with all this advancement comes a few other considerations, right? We have governance and then we have ethical AI. So governance is the policies, the regulations, the practices, and tools aimed at ensuring that AI systems are actually ethical and safe and transparent and accountable. As they get smarter and smarter, we have to make some rules around them. And so there's guidelines for the responsible development and use of AI across industries with the goal of creating trust in AI by putting some checks and balances in place. So this happens through both government regulations as well as self-governance within organizations and within the tech community. And then there's also a whole conversation around ethical AI. We actually had a whole panel really about it in our Women in Data Science conference a couple weeks ago. And ethical AI is really the artificial intelligence systems that are aligned with moral and ethical values like fairness, accountability, transparency, privacy, safety, right? All of these things. I think we had just because we
can, should we?
Right, should we?
Yeah.
And so that's definitely a conversation that's going to grow and grow over time. And I'm sure we'll be hearing about it in the news constantly.
Awesome. So that wrapped up the general presentation we had. We have time for just one question, and someone had posed in when Kathryn was going over the generative AI slide about hallucinations. And so I wanted to speak to that actually more broadly. So hallucinations are when generative AI models get things wrong, where they basically make up text, they make up output. But I think more broadly, if I leave you with anything, is the understanding that any model can be wrong. So not just the ChatGPT model, any model, the house prediction model can be wrong. The Spotify playlist model can be wrong. So you as a human needs to decide if you're okay with the risk of that model being wrong. So if I recommend, a bad song to Kathryn, what's really the downside risk if I'm Spotify? nothing. Like if I do
Pretty
that
much
too many
nothing,
times,
right.
she might get annoyed, but probably nothing. If I am suggesting who gets funding, if I'm suggesting who gets medical care, if I'm suggesting all of these much more human impact type things through a model, well, if I get that wrong, that's probably not great, right? So you as an informed user of these models now, after attending our session, should always challenge and think about the output. Is this right? Does this make intuitive sense to me? How is this being used? Is this really the right place to be used? Just because you can build a model does not mean that you should deploy that model. These are all things that you all have control over in both your careers as well as your personal lives. So I'm going to leave you with that. Thank you all for having us here. This was absolutely fantastic. Please feel free to connect with both Kathryn and I on LinkedIn.
Thanks, everyone.
Thank you both, Erin and Kathryn. I think if you're open to it, we have some extra minutes to answer the other questions if you're open to it, if you want.
Yeah, absolutely.
Yes, perfect.
Yeah, we're happy to stay on a couple extra minutes here. So we answered the hallucination one. So at what point do you consider a label as a classification or as a variable that just changes sporadically? So for me, when I'm thinking about what is a label or not, it actually comes down to my definition of the use case. So the label is what I'm trying to predict. So the label is I'm building a weather model, the actual temperature outside that I'm trying to predict. If I'm building a computer vision model, what am I trying to identify in that? So the label in that case is actually what you want your prediction to be. So if you use that as a definition, hopefully it might help you kind of differentiate between if it's a variable or if it's a label and how you deal with variables changing over time. There was one other question on, did a change in infrastructure play a role in a move from AI winter during COVID, the COVID pandemic in particular? So I assume this might be alluding to how people were potentially working from home during COVID. A lot of AI, I would say AI resources are all cloud-based today that can be kind of accessed from pretty much anywhere. We actually do a lot of our development on-prem, so on site on our own servers, but with the infrastructures, the technology infrastructures that we have today, I wouldn't say that kind of that move to potentially working from home, not being in an office, had any real play on any sort of AI winter. I would say if you saw any sort of kind of, slight receding in AI investment during COVID, is that we were all kind of just distracted, especially in the beginning, by other things. So it was more we were trying to keep the lights on as opposed to actively saying we're not going to invest in AI. We definitely went through that, especially in the first year, that kind of a lot of our AI models just got put on hold. We knew we were going to come back to them, but at that point we were just kind of trying to figure things out. And there's one other question that I'm going to answer, and then we're going to cut it off there. But you did mention AI winters. Seems to me that, yes. Okay, so this is a great one. Seems that some believe there is one coming because there's a dwindling amount of available high quality big data sets to train these models. And absolutely, there is, I'm hoping that we're going to bypass the AI winter by pivoting from just making ChatGPT 5 bigger than ChatGPT 4, right? And how they're really doing that today is by just getting more data. I'm hoping that we're going to pivot from this, we need more data, we need more data, we need more data, we need to make these models bigger, we need to make them bigger, by pivoting them to use cases. So a lot of use cases of a ChatGPT today is still kind of, you're playing around with it, right? Very few companies have actually implemented this to make humans more efficient. I'm hoping we pivot that resource, bypass the AI winter by saying, okay, now that I have these tools, let me stop making the model bigger and worrying about more data. This model is good enough. Let me start investing in helping to refocus human energy on places where we add value. So humans still will have a big role in the economy, in every field. There's still places where human interaction matters. You want to talk to your doctor, you don't want to talk to a robot, right? So I'm hoping that we can pivot and bypass that by just redeploying these models that already exist today and making us all more efficient to focus on higher value tasks. Awesome. So thank you everyone for today. This was fab.
Yes, it was amazing. Thank you both.
Oh,
I mean, it was really empowering. It was really captivating. The audience just said that they were here during the full hour, really interested in everything that you're
good.
doing. So that's perfect. And also you even added, I love it that you even added a plot made with ChatGPT for your presentation.
Yes.
So that's perfect. It's a perfect example of how to use this. And I think you covered so many important topics in AI, gave us a really well-rounded view of AI, what we can do with that, and it's going to be very, very helpful for anyone wanting to enter into this field. So thank you very much, both. It was really, really exciting and very interesting. So
Awesome.
thank you for an amazing workshop.
Thank you, everyone.
Thanks.
Thank
Bye.
you.
Bye.
And please tune in to our next workshop that is going to happen next Wednesday at 8 a.m. We're going to have a workshop presented by Garima Sharma. The title is Local Low-Code Data Analysis for Excel Users using MATLAB. And also on behalf of the WITS Workshop Committee, thank you to all the instructors and thank you to all the committee that helped organize today's event and the other events for the WITS workshop happening every Wednesday. We're very grateful for your time and for your effort. And also, finally, thank you, the audience. If you can take a couple of minutes to answer and to fill in our short survey, we are going to be very grateful. And also, if you answer the survey, this is going to help us optimize these workshops for you. You can use the QR code on the screen. And also, you can use the QR code on the screen to apply to lead a WITS workshop in the 2024 season. And that concludes today's WITS workshop. See you next Wednesday.